All right, hello my friends. We're going to cover project 2 and just how to get everything set up. So first thing, let's create a project as usual. So project 2, and then just make sure to put it somewhere that is good for you. We'll go ahead and do that. Just click next, next, next. We're not going to use any sources for now. For the part, I'll just click the one that I just used, which is this one, and then finish. So all we have to do is create a block design. So block design, just name it whatever you want. And yeah, so then let's also add the constraints file just so that we don't forget this later on. So add or create constraints, add files, and go navigate to the Git repo. So wherever you cloned it, there should be an XDC file here. Just copy it in there. That's fine. If you don't want to copy it in, you can edit it from what's it called, VS Code. All right. So what we're going to do just to start is we're going to start by adding the Microblaze processor. So you just add by clicking the plus, click Microblaze, and we'll click Run Block Automation. So you can change a lot of stuff here. You can change how much memory it has, and let's just add as much memory as we can for now. I don't think we're going to run into any issues, but let's just start there. There's debug modules that'll come with one. We want this peripheral AXI port, because we want to interface with AXI components, just like we talked about in class. So we're going to keep that on. There's an interrupt controller. Usually interrupts are good. You want to have hardware interrupts such that when something detects a change, it sends an interrupt to the microcontroller so that it does some type of interrupt service routine. But just for simplicity, we're not going to do that yet. So we'll not worry about that. And then for clock connection, click New Clocking Wizard, click OK. So this will create some components for us. You'll see it'll start spawning on the layout. There's the memory, processor, system reset, as well as this clocking wizard and the debug module. The most important thing, and you can click this regenerate layout button to lay everything out, is this clocking wizard. So this is the PLLs, the phase lock loops of the FPGA. It creates different speeds of clocks for our design here. And the clock that it takes in comes from the FPGA itself. And so we have to configure it such that it takes in the correct clock source. So you look at the primary input clock, and it's supposed to take in a 100 megahertz clock, which is right, that's what the board gives us. But the source is a single-ended clock capable pin, so we have to change it from differential to single. And you'll see that it changes the port there. For everything else here, you see if you wanted to add extra clock speeds, if you wanted to create new clocks, you could do that and request different clock speeds, and then the PLLs would give you those. For reset type, we're going to use one of the buttons on our FPGA. So we're going to keep it as active high because that's how the buttons are. If the button is unpressed, it's 0, and if it is pressed, it's 1. So when we press the button, it'll turn 1. So that means that we want to reset when the button is 1. So that's why we want active high. So click OK, and then let's click Run Connection Automation and just automate everything. So do that. And then one thing I'll do is I'll just change this reset signal to be just reset, just like that. All right, so now we're done with our actual Microblaze. We have to add some peripherals to this though. So the first thing that I'm going to do is I'm going to add a UART module. And the reason why is because we want to be able to send print statements, data from the Microblaze, communicate with it. So having a UART module is very helpful. And the way that we do this is we start by adding an AXI interconnect. So you can search up AXI Smart Connect. That's what it's called in Vivado. Basically, you attach your peripherals to this Smart Connect, and then the microprocessor will communicate via this AXI bus. So we can configure it by saying we want one slave, meaning and the slave in this context is the processor, and the master interfaces are the amount of peripherals that we want. So for our design, we're going to want a UART, we're going to want LEDs, switches, What else? I think that's it. Yeah, that should be it to start. So we want at least 3 masters. So we click OK, let it go through. And then we need to connect it to all of the clock and reset. So what you can do is you can drag it from clock to any of these clocks. They're all the same basically. The reset, so this is an interconnect component, so we're going to connect it to the interconnect reset of the processor system reset. And then we need to actually add our component. So what I'll do is I'll search up AXI UART, and so I'll click AXI UART Lite. We could do run connection automation, but probably better to do it manually so you see what's going on. So, oh yeah, we also forgot to connect the Microblaze to the interconnect. You could, of course you could connect to the Microblaze directly to a peripheral, but then you can only communicate with one thing, and that's obviously not what we want. So let's connect it to the Smart Connect, and then all you have to do to connect our peripheral to the AXI Smart Connect is just drag a wire between them. That's good. Connect the clock to the system clock, which is all the same, and then attach the reset to the peripheral reset, and because it's active low, which it says A reset N, you want to connect it to peripheral A reset N. Alright, and then lastly, you just have to click on the pins for the UART and click make external. And I'll just rename this just to UART so it's simple. Alright, so that's step 1. Now we've got 2 more components that we want, so I'm going to add the AXI GPIO component, and this will allow us to interface with switches pretty simply. So let's drag it over here. Oops. Let's drag it over here. And let's connect it to the second guy over here. Let's connect the clock to any of the clock wires, and then the reset to the peripheral reset. It'll show a reset with the AXI UART, so that's easy enough. And then we have to configure it. So we're going to use the AXI GPIO component just for the switches. And I'll explain why in a second. So what we know is that all the switches are just inputs, right? So we can click all inputs, and we know that there's only 16 switches, so we'll just type in 16 for our GPIO width, and then be done with it. So you do that, and then make the pins external, and I'll call these SW for switch. And so to access the LEDs, we're going to use a different protocol called APB. And you've learned in class that AXI is a very high-speed protocol to communicate with peripherals, but if you have too many things running on an AXI bus, you get throughput issues. And you really only need like the most critical parts of your SoC to be using AXI. Anything like GPIO, and I know we're using switches with the GPIO AXI component, but we're just trying to give you an example. Let's say that LEDs they're not as important for the design. You don't need them to have like high throughput data communication, so we use another slower peripheral bus called an APP bus that handles requests to the, like in our example, the LEDs, but just in a slower way, and kind of frees up some space on the AXI bus. And so the way that we'll do that is we'll search up APB, and we'll create this component called an APB bridge. So AXI to APB bridge. We'll configure it a little bit, and we'll say we only have 1 slave because that's how many peripherals we want attached to our APB, and we just click OK. And so just like the Smart Connect is an interconnect for all of the AXI peripherals, this AXI APB bridge is an interconnect that connects to the other interconnect that then will attach to more peripherals. But again, there's kind of layers of isolation. There's the Microblaze, there's the AXI bus, and then even further below that, there's the lower speed APB bus. So we attach the clock to the same clock that everyone else has. The reset, this is an interconnect, so we're going to attach it to the interconnect reset. And then for our peripheral, well, we've provided you an APB peripheral here because they don't really give you those. But you can do it, you can add it by going to the IP catalog, clicking add repository, and then go ahead and find wherever you made it, or wherever you cloned your repo. So I have it in here for now, but for you it'll be inside your Git repo. Alright, where did it go? No, it's not there. It's in the APB LED one, right? There we go. So now that we have our APB component, we can add it by searching it up. So APB LED controller, and this will give us access to all 16 LEDs and then the RGB components that we've got. So we need to attach it to the clock, the peripheral clock. We need to attach it to the reset for the peripherals, and then we need to connect the APB wire straight to the APB interface that our APB component is using. And then we need to expand these pins out. So we click make external on all of them, and then I'll just rename them to something more simple. So that's LED. I'll just name this RGB0 and then RGB1. Okay. And I'll reload everything. And so I guess one thing to consider is that the reset of our button is active low or is active high. So we need to change the reset pin on our device. So we have to say active high pin, and let's reload everything. And now that that's active high, this is expecting a reset in of low. So it's expecting an active low pin. So what we need to do is disconnect this wire, and we need to add a vector utility logic or whatever it's called, and then put a NOT gate on this reset button. So we'll do NOT, make it 1 bit, drag the reset, and then I'll reload everything. And there we go. So now we have, on the AXI bus, the UART, the GPIO for the switches, and then on the slower APB bus, we've got the LEDs, RGBs, and that's it. So we should be done for our main hardware design. Now the big thing is how do we actually do the pin assignments, right? Because there's stuff like this, like the UART RXTX. Like we don't actually know what the name of these pins are. Same as the GPIO. It just says like GPIO something something. So we need to create the net list, which is what will actually tell us how to name our pins. So let's go ahead and click Open Elaborated Design. And oops, I forgot to convert our block diagram into an HDL wrapper, so you have to do that first. So this might take some time because there's a lot of components. It needs to generate HDL for every single thing. And we can click background. And I think one thing I may have forgotten was the addresses. So let's check that. So there's this thing called the address editor up here that basically tells you where all of the components that you have are assigned in the address map. So yeah, I forgot to do that, but basically, we've got the AXI UART, the AXI switches, and the APB LEDs. We need to assign those addresses in the memory of the Microblaze, because we're using memory mapped IO. So we go to the address editor, click this down arrow, assign all, and that goes ahead and assigns, the GPIO switches, the UART AXI, and the APB stuff to these memory addresses, such that when we write to those memory addresses, we'll have the ability to control them through the software. So this is the memory map of our device, so that's good. So let me reopen the elaborated design, and I guess we'll see what happens. I'll click background so I get some extra time. I'll just inspect my thing just to make sure everything looks good. Just make sure all your things are connected. Should be fine if you followed along so far. And as I was saying, you can use the interrupt controller, add interrupt stuff to these components as well, such that the processor doesn't have to pull things, but that's going to add some level of complexity that we don't really need right now. So we'll stick with this. And yeah, so it's going to generate everything, and hopefully it'll be done in a second. Yeah, and so this reset, processor system reset, there's so many wires here, but really it's just to make sure that timing is met when you reset everything, so that the resets reach every component at the exact same time. So you don't want things to reset at different times and have some undefined behavior. You know, that's really important. The debug module, this will allow us to actually debug our software on the chip without actually, you know, having to buy a debug chip. So we actually have a debug chip that's put onto the FPGA fabric, which is great. The local memory, it's all here. It's really easy. You don't even have to think about it, which is really, really nice. And yeah, so this is taking a while because I guess it's trying to compile all the code for the Microblaze. So we'll see, I guess. Could take up to like 20 minutes. So I'll pause here and then I'll come back when it's ready. All right, I'm back. I was able to go eat dinner or lunch in the time that it was taking to synthesize. So yeah, it'll take a bit of time. That's not a problem. All right, so now that we've opened up the elaborated design, you know, it's got everything inside here. I mean, you don't really need to open it, but it's elaborated our stuff and it's given us the actual pins that we're going to be using on the board. So we can see the names here, which is great. So that means that we need to go ahead and assign the pins as per this list here. So the first thing that we need is the clock. So clock 100 megahertz, it's already named that, which is great. If it was named something else, we would have to change this, but we don't. So you can do control /, that'll uncomment this stuff. We want all of, these LEDs. So we can just uncomment all of them. And the LEDs are already named LED 0 through 15, and that matches exactly what we have on the schematic, which is great. The RGBs, we can uncomment that here. So as you can already tell, I've named them like that just so that they would match the thing here. But if you wanted to change the name, you would just retype them. The reset pin, we want to attach it to one of the user buttons, so we'll attach it to the first button. So let's uncomment that, and then let's change the name of button 0 to reset. Right, and that's going to match this thing. For the switches though, we're going to have to rename them. So the pins are named switch underscore try underscore I. So we need to uncomment all of the switches and then rename them from SW to SW try I. And I mean, I don't really know how to type in multiple lines here on Vivado, but you can just go ahead and go down the line and assign them. So let's keep going. And that should be all 16 switches, so that's good. And then lastly, we have the UART, RX, and RD. Sorry, TX and RX, I don't know what I'm saying. So we need to scroll down and go find that. So if we look here, line 146, there's the UART. So let's just uncomment them. They should already be, if you named it this, then they should already be in the right order. So you can, we don't really have to change anything there. So that's good. So let's save. Can reload it, but I don't think that really matters. So, because we're about to do generate bitstream in any case. So we just go ahead and click generate bitstream, and yeah, and I'll be back when that happens. It might take another few minutes. All right, we're looking good. So bitstream successfully completed. That's great. I guess I'll just open up the implemented design, see everything that we've built. Excuse me. And so once we've designed our hardware, we're basically done, unless we want to add more stuff, right? That's something else. But for now, we're done. And then we can move on to the other software, which is called Vitis. So what we do is we do File, Export, Export Hardware, click Next, and then click Include Bitstream. You can name it whatever you want. I'm just going to keep it as Design1 wrapper. I'm going to keep it in the default folder. Click Finish. And then we'll go ahead and click Tools, Launch Vitis IDE. So hopefully this doesn't like blow up my whole computer. But what I'll do is I'll create a workspace. So I'm going to go into the project that I was just in, which is project 2 SOC. I'm going to create a folder. I'm going to call it Vitis Workspace. Oh, Vitis underscore WS. It can be whatever you want, but that's what I'll do. Click Open, and then click Launch. technically, since I don't need Vivado anymore, I can just close it out. So let's close that out for now. Might help save some RAM on my computer. Oh, that doesn't look good. Well, I'll just close that up. I'm not sure what's happening here. I guess that's Linux for you. So what we need to do is we need to click Create Platform Project. Seems like it's not loading up, so maybe I'll have to open it up. I guess because I launched it from Vivado, kind of broke, but whatever. You can open it up just directly. Oh, that actually works. I guess I don't have Vitis on my path anyways. So again, create platform project. I'm going to name it project 2 SOC, doesn't matter. And then we'll click, it'll say create a new platform from hardware, XSA. So that's the file that you exported. So you just click browse, go to the folder where you made the project. So let me find it. It's not where I put it. It's in my Vivado 2021 projects, project 2 SOC, and there's the XSA. So you don't need to change anything else. It should say Microblaze processor. That's good. So click finish. All right. And then now that we've done that, what we need to do is click build. So we need to build the platform. All right. Sorry, I just realized I was supposed to click application project. So I'll just click file, new application project, next. So, once you've created the platform like we just did, you'll just click project 2 SOC or whatever you named it. It should say Spartan 7 with the right part. That looks good. So we'll click next. Project name, project 2 SOC. I'll just call it project 2. It can't be the same name as whatever your platform is, so just name it something else. Standalone, that's fine. And then we're gonna click on this Hello World template. There's a lot of other stuff here, like empty application, but we'll use Hello World because that's gonna be a good start. All right. So now we have loaded up a bunch of the C code that we're going to program onto our Microblaze. We can see that by clicking on source and then hello world.c. This is the entry point to our system. Okay. So all you have to do is essentially click on the project 2 platform, click build. Okay, it says nothing to build because I guess I already built it, but for you, you'll have to build it. Then the next thing you do is you click on the application, click build. It says build finish, so we're good. And this is just to start. So what is this doing, this hello world.c? So it's running some print statements here. And what is it using to, like, where is it printing to? Well, we're programming the Urbana board, and the Urbana board is going to send stuff over UART to us, meaning our computer that we're using right now. So we're going to need some type of tool such as PuTTY. So PuTTY SSH client, or you can use anything else that you want. This one you probably have. You'll have to connect it to serial. Now, one way that you can find out which port you're on is if you're on Windows, you can go to Device Manager and then look at like the all of the USB devices, and it should say like COM1, COM5. I don't know. It's like COM with a number, and you would type it in like this, or COM2 or something like that, and then you set it to 9600. I'll tell you it's 9600 because that's what we set it to. That's what it is by default in what's it called, in the hardware design. So that's how you do it. If you want to make things bigger too, you can go to fonts, change the size by clicking on another one and clicking a bigger font. I already have something loaded for the Urbana, and I know that I'm on this TTY because if you're using Linux, you can just search up which device, or I know that my device is this FTDI thing because I plugged it in and instantly did this command, and then I could see that I'm on USB 0. It usually opens up 2 ports, but the first one is the one that you want, and you'll know it's right if you open it up and it works, but clearly that didn't work. So let me try and restart the board. So I've got the board plugged in now. Everything's green. So let's open up Urbana. All right, and looks good. So the UART port is open on the board, and so we can see on the actual screen, PuTTY is connected. Obviously nothing's happening because we haven't programmed it yet, but we'll do that now. So I move this over to the side, and then I'll keep PuTTY open on the side here. So what we should see is we should see hello world successfully ran hello world application. I'll just put a new line here on the hello world line just so it prints out a little nicer. And then every time you make a change, make sure to do build. So build finished. And then what we need to do is click on system, program device, and then everything should be fine. So just click program, and then we pray that everything worked well. Everything is working, and it'll go through. Seems like it blew up my board, so that's not good. So, okay, I think I figured it out. I think it was actually on the other port, but I mean, you can try this out, and whichever one works. So I was using USB 0 before. I'm gonna switch it to USB 1. So I guess I'll just load this config, save this, and then I'll open it up again. So now it seems to be fine, so we'll just run it. Let it program the board. There we go. So that means that our board, our Urbana board, was programmed with the microprocessor running the code that we have here, and then it sent back to our computer, this hello world application, and we could change it quickly right now, and just to verify. So my name is Newman. I'll save that, and then rebuild. So you can, I guess, click the hammer up here or wherever you want. Make sure you do that, because if you forget, it's not going to work. Click the play, or I guess up here, wherever you want. And it should reprogram it, and it has our new code, which is really cool. Another thing that you can do is debug. So you click on the debugger, and you can add breakpoints. So let's say I want to toggle a breakpoint when it's printing hello world. We should be able to click resume, and it'll keep going until that first line. Well, I guess it sets up the print, but it won't print until the next instruction is done. So it prints out that first thing, and then only once we resume again, it'll go to the next one. So that's what that debug core was for at the beginning. So that's really, really simple. And it's really powerful, because now you can actually debug your code using this IDE, which is great. And so now the program's done, so it disappears. So now let's do a very simple application where we access our peripherals. So this is not that useful for us, a hello world thing, but this is something that you'll have to do. You're going to screenshot your thing working, and ideally put your name there. I think that's in the instructions. So let's get rid of this. We don't have to change anything. Let's just get rid of whatever the code was in there, and I'm going to pull up some new code that I wrote up just really quickly, and then I'll explain how it works. So here's the new code that I have written that will access our LEDs and switches, and basically do something, and I'll explain that. So the first thing to note is that you should keep the standard IO and platform H just like we're in the hello world file. You'll include this printf file if you want. I think that was already there actually, so you don't need to worry about that. It's these two that you really want. So xparameters.h and xilinx.io.h. I don't know if I can zoom in anymore. I don't know. I guess I can't. Let's see. No, I can't. That's unfortunate. Oh well. So the first file, xparameters, if I double click on it, open the declaration, it's got all of this stuff inside of it. Okay. It's got a bunch of like definitions, and a lot of this stuff is not really useful for you, except for the addresses of the peripherals that you created. So if you go down, there's these peripheral definitions for your APB LED controller, as well as your GPIO. So you look for the one that says base address, and that's the one, this is the address that was assigned in Vivado. So when you try and write to that address, it's going to write to the register that controls those peripherals. And so what you'll see in the C code here is I've taken those variables from the X parameters file, literally just copied this, Control C, and then put it in here, and then renamed it to LED's address and then switch's address. And for any other peripheral that you have, you need to go in there to the X parameters file and find them. This is all generated for you when you build the platform from your XSA hardware description file. Next, I just did the init platform function that's given from Xilinx. The print function just to say that we're starting. And then big thing, so for those of you who have taken microprocessors, you know that you usually want to have an infinite loop that does something, because if otherwise the program goes through and then just ends. For us, if we want to have something that goes on all the time, we need to have a while loop, and in C, you just do while one, meaning always go. You could also have break statements in here if you ever need to have conditions where you break, but if you reset the board by clicking on the reset button that we've assigned, it should do the same thing. It'll break you out of that loop. The first thing we do is we define two variables to hold the values of the switches and LEDs. The reason why I've assigned it to 32-bit size is because the registers that they are memory mapped to are 32 bits. So even though we have a 32-bit register, and our switches we only have 16 switches, so it's only using half of the register, we still want to read that whole thing, just to make it simple, because every register is 64 bits. Same with the LEDs. We've got 16, but I've just assigned it to a 32-bit variable. The top 16 should be all zeros, ideally, but we'll see how to do this. So the switches, what we do is we use this Xilinx in function, and you notice here it says the type that it's reading in. So it's reading a 32 bits of data from whatever address you pass into it. And you can find out what other types of functions you can use by opening the declaration or definition. Let's see. Let me get out of the debug thing. Let's open this up. Open declaration. Whatever. I'll just click on here. And you'll see this file, xilinx._io, which is one that you included, has all these different functions, such as reading in 32 bits, reading in 16, and it tells you what type of thing it reads. Well, it just reads some value. Since we know that it's returning a 32-bit value, and switches is a 32-bit value, we know that switches will just have the whole value of whatever the switches are right now, right? Because we're reading from the address where the switches are mapped to. Then with the LEDs, we can do something. So in this example, I just have LEDs equal to switches, and then I do this type of bit masking where I'm saying, okay, the bottom 4 bytes, which is the bottom 16 bits, we want to keep those. Any other garbage value that could be in that 32-bit register where the switches are, get rid of that. Just get rid of it entirely, okay? And so that's what I've done here. So basically anything from bit 17 up to 31, those will all get wiped away. And this LEDs, this 32-bit value will be a bunch of zeros, 4 bytes of zeros, and then 2 bytes of zeros, and then 2 bytes of whatever the values are. And then we want to write to the LED address, like write to the actual LEDs with the value that we want to send to the LEDs. So what does that mean in this case? Basically, whatever the values of the switches are, they're going to get mapped to the LEDs, and thus what we should see on the board is if I turn on a switch, the corresponding LED will turn on. Okay, and so let's program this onto our board. So make sure to click build, and then we'll program it. So I don't really want to debug it, I just want to program it. So I'll just click program device, program. So let's find out if this works. Okay. So it's loading up. Okay, so right now nothing is on because all the switches are low, but if I turn on some switches, okay, that's not working. Give me a sec. All right, so lesson learned. I was just trying to figure out what I did wrong, and I was holding my finger on this little component that's like near the power button, and I did not realize, but you can actually short out those things. Like as soon as I pressed my finger on it, because I was holding it like that, trying to show it to the camera, and I heard like this little screeching noise, which does not sound very good. I think something was getting shorted out, so it actually was like causing my thing to not be programmed. So we'll try again and see if it works now, but let's find out. Yeah, so starting application, that's exactly what we expect from here. Okay, I thought I did something wrong, but we're actually okay. So now, let's flip some switches up and down. So now you can see that the switches, when they go up, they get mapped directly to the LEDs. So there's no direct connection between the switches and LEDs. The switch values get read from the microprocessor reads them out to the LEDs, etc. And if we want to make changes to how this logic works, it's so easy because now we're working totally in software. So let's say that we want the LEDs to be on if the switches are on the bottom. All we would have to do is just change the variable that's being written to the LED thing. So I'll just change it to invert all those switches, rebuild it. Again, make sure to rebuild it because I forget sometimes, and then rerun it. And this time they should all be on. Yeah, they should all be on. And then when you flip them up, they turn off. And so this is very powerful because you could do any type of logic you want here. But this is at least hopefully enough to get you started with the rest of the project. But this is how you do it. And if you add more peripherals, which you will, make sure to go in the X parameters file to find those addresses and use these functions that Xilinx gives you to write to those memory addresses, so you don't have to deal with like raw pointers, because that's pretty bad, honestly, and actually quite complicated. Very easy to make mistakes. So with that, thank you for watching, and hope that you are able to complete this very easily.